All right, we're still moving, still grooving, still shaking, still baking. Oh, yeah. I'm now going to flip over to level 3. And okay, well, for a minute there, I thought level 1 and level 3 are the same problem on the back. No, but they're different. Okay, so level 2, 2,200 kilogram car. Okay, let's look at level 3, problem number 1. A 3,000 kilogram car starts from rest. Sounds similar to the problem we just did, but it's not. Okay, so let's see. Let's write this down. Level 3. Level 3, problem 1. After 3 seconds, the car is moving at a velocity of 9 meters per second. There is a retarding friction force of 500 newtons acting on the car. Retarding means to slow down. Okay. What is the power needed by the car in order to accelerate it from rest to its final velocity? Power. This is a little different than that last problem we did using engines and cars moving. This is a power problem. This is a horizontal power. The last time we just used work and kinetic energy to figure out velocity. This time we're figuring out the power. So let's take a look at our equation. Power equals work over time. Now the nifty cool thing about physics, besides like everything is nifty cool about physics, is that you can take equations and make new equations out of them by substituting in other equations. Let's do that. And let's just see how that might help us in this problem. Work is force times distance. What is force? Most important equation in physics 1. MA, thank you, MA. So force is MA, so that's mass times acceleration times D. Are you mad? Divided by time. That's a different way of writing the power equation. We could also look at it and do this. That MAD over T, D over T, distance over time, distance over time, distance over time. Distance over time is velocity. So we could write this as MAV, distance over time is velocity. MAV, crash and burn, MAV, Top Gun, 1986. Right? Okay, so we have different versions of the power equation, and sometimes one is more handy-dandy notebook than another one. So let's take a look at this problem and see which one we might want to use. Okay, we have the mass of the car, 3,000 kilograms, 3 seconds, so we have a time, 3 seconds. The car, after 3 seconds, the car from rest, so initial velocity is 0, final velocity is 9 meters per second, and there's a friction force of 500 newtons slowing this thing down. So here's what we have to do. This is a different problem than last because of one we're figuring out for power. But this one we got to think a little differently. This is why it's a level 3 problem. A little harder than the level 2 problem at the top that we just did because we have to think about this. The engine has to do 2 things. 2 things? 2 things. It has to overcome the friction that's saying, no, you shall not pass. Friction is like Gandalf. Some of you get it. Okay. And the friction, besides the engine overcoming the friction, it also has to accelerate the car with these conditions. We know the car is accelerating because it started at 0 and went to 9. So we know the engine is accelerating the car, but at the same time, it's overcoming the friction. It has to provide the power to do those 2 things. And we have to use both of those things in the power equation to figure out what is it? We figure out power? I forget. Let's see. Yeah, what's the power needed? So we're trying to figure out how much power that the engine has to provide to do those 2 things, overcome the friction and provide that accelerating force that we get the car going to 9 meters per second. Okay, so which one should I use? Well, let's see. We have mass. So one of these looks pretty promising right now. We have a time period. Okay, well, time period's here. Time period's here too, which is kind of hidden. All right, well, what about velocity 0, velocity of 9? That means the car accelerated. This shows that the car accelerated. So, I don't know. This is looking pretty promising, this one too. I'm looking at one of these 2 because it tends to have the stuff that dreams are made of to solve this problem. Mass has an acceleration. Now, not a direct acceleration. We're going to have to figure that out. We'll have to figure out the acceleration. Yes, we will. We'll have to figure that out. So we will have to use a kinematic equation to figure out the acceleration, but we're using the power equation to get the power. I mean, that makes sense. If you're going to figure out power, you got to use the power equation. But we have to use the acceleration equation to get the acceleration so I can put it in the power equation. So let's do that right now. I need the acceleration. I know that because it shows up twice, and I know the car is accelerating. It's going from 0 to 9. Okay, that's a difference. Remember, your acceleration is change in velocity over time. Change in velocity is 9. The time is 3. So my acceleration is 3 meters per second, 3 meters per second squared. All right? Now, there are actually two ways to solve this problem. You could use this equation or this one. I know most of you are probably thinking, I'm going to use this one because it looks easier. Actually, there's a concept you'd have to think about to use this equation. So let's hold off on that one, and I'll show you why in just a minute. Let's use this one. Trust me, okay? I know I'm not wearing a tie now, so you can trust me. I think in the earlier video I said don't trust me because I'm wearing this shirt, but whatever, trust me. Okay, so now this mass times acceleration is the force that the engine has to provide to accelerate the vehicle. But there are actually two things that the engine has to provide force to do. One, to accelerate the vehicle, and the other one, to remember, overcome that friction. And if you look back into the problem, the friction is given as a force. It's given as a force that needs to be overcome. So what I'm going to do is figure out the force needed, m times a, to accelerate the car. Now, if there were no friction, then I still have to provide that force to accelerate the car. I still have to provide an m times a amount of force to accelerate the car. But then in addition, I have to overcome the friction. So the engine has to do two things. So this time, I'm going to add the force of friction that I have to overcome in order to accelerate the vehicle. The engine has to overdo, once again, two things the engine has to do. Accelerate the car, and overcome the friction. That's weird. So we're so been ingrained at this point to take friction and subtract it from something and get a net amount of force. But in this case, no, this is actually a different problem because we're not trying to figure out what the overall forces are. What we're trying to do is figure out how much force the engine must provide. And the engine must provide an accelerating amount of force, and it must provide enough force to overcome the friction. So in this problem, we add the two, hence the level 3. That concept, not so easy. So we're going to have to take the mass times acceleration, add to it the amount of force of friction that we have to provide, then take the distance that we've traveled and divide it by the time. The distance that we traveled, well, wait a minute. We haven't figured out the distance that we've traveled. Exactly. So we've got to figure that out as well. Oh, this is probably a lot more complicated than we thought. So the distance that we travel, well, we can use a kinematics equation to solve for that. Distance is equal to VIT, but the initial velocity is 0, so that's gone. VIT plus 1/2 AT squared. Okay, so let's figure out how far the car would go in this 3 seconds of time. What distance did it travel? So 1/2, acceleration is 3, times time, which is 3, squared. So 3 times 3 is 9, and 9 times 3 is 27, and then 27 multiplied by 1/2 is 13.5 meters. So the car would have traveled 13.5 meters in this amount of time with that acceleration rate. So now I've got the distance, I have the time. I am actually at this point set to solve the problem. But again, it's level 3 for a reason. There are several things we didn't have in the last problem where we had a car going down the road. Okay, let's do it. Let's figure it out. We can do this. We're relatively intelligent people. Well, I'm not. You probably are, though I'm not. I'm kind of dumb. All right, now power equals mass. Oh, crap. I just erased it to make room, but I don't remember. 3,000. 3,000, see, not so smart, times acceleration rate, which I do remember was 3. Now, That'll give me the amount of force that I need to accelerate the vehicle. And I have to overcome the force of friction, which was given as 500. Okay. The distance that we traveled while this thing is accelerating was 13.5 meters. The time that this whole thing takes place is 3 seconds. So I'm going to do the math on that and see what we get. Okay, so this is 9,000 plus 500. So 9,500 times 13.3. It's 13.5. And actually divided by 3. So right now, well, that's a hard one. It's 3,000 something. I won't do it. I just do it out. So let's do the math. Okay, so 9,500 times 13.5 divided by 3 enters 42,750. 42,750. This is power, so it's going to be watts. That would come out to be joules per second. I'm not going to do a unit analysis on that. Trust me, it does come out to be joules per second. 42,750 watts of power the engine would have to provide to overcome that friction and to accelerate the vehicle at that rate. Now, it's not a lot of friction. It's only 500 newtons, but it does make a difference. If we take that out, we don't put that in, we get a lower number, and it's not correct. Okay, not a lot lower, but a lower enough that we would say, nope, no. Now, go back to this equation back here. We can use this equation to solve the problem. Some of you might be saying, well, yeah, why didn't you do that? I mean, it looks easier. My gosh. Okay, let's go back to going ahead and doing this. Remember, this is force. That's force. So power equals mass times acceleration plus, you still have to add the 500 newtons due to we have to overcome the power to overcome the friction, the power to accelerate the vehicle, times V. Okay, let's go ahead and do it. So mass, 3,000. The acceleration is still 3. This is 500 times V. This is 9,500. 9,500 times V. And we're good to go. And so you'll be saying, well, just put the velocity in. Put the 9 in there. And that's it. It's easier, right? It actually is easier, but there's a concept here that you have to realize, otherwise you'll get this wrong. Let me show you. So let's say that we go ahead and put the 9 in there for the final velocity. So 9,500 times 9, 85,500. That wasn't 42,750 that we had in the last problem. That's wrong. It's right. It's wrong. Well, what's the concept? The concept is the car starts at 0, ends up at 9. So during the time that it's accelerating, its velocity is changing. So which velocity do I use? If I use the ending velocity 9, clearly it's wrong. We came out with 80-something thousand. That's not the answer. If I use 0, well, anything times 0 is 0. That's not going to work. We have to use the average velocity. Assuming that we have a constant acceleration rate, then the average velocity can be put into this equation and solved that way. So the average velocity between 0 and 9, okay, let's get the average. We'll take those two, 0 plus 9, and divide by 2. Anybody have a calculator? Okay, that 0 plus 9 is 9, divided by 2. Anyone? 4.5. The average velocity during that acceleration period was 4.5. We can use that. So we could put in the average velocity, 4.5. Now you multiply that by 4.5, and I bet you batoot that we will have the exact same answer that we just arrived at. Boom! 42,750. You don't believe me? Believe the calculator. All right, yes. So we do get the same answer, but we had to, and that is an easier equation to use to solve this problem. You don't have to figure out the distance you travel. It eliminates the time on the bottom because it's It's wrapped up in the velocity, but you have to use the average velocity of the acceleration period. Okay, that solves a difficult problem, but it's okay. It's all right to be challenged. Take the physical challenge.